So some things to highlight here. Okay, we talked about all right, so right here. The binary ionic naming. The name of the metal keeps its name. The anion, the nonmetal, has an IDE end. Okay, so this is for the alkali metals, the alkali earth metals. All right. Metals where the oxidation state does not change. Okay. Polyatomic ion name. The name of the metal keeps its name. The name of the polyatomic ion keeps its name. So that means you need to know polyatomic ion names. So I gave you this list of polyatomic ion names that I generally recommend that people know. Okay, you already saw some of these in the practice problems. Sulfite, sulfate, hydroxide, acetate, ammonium. Okay, so the polyatomic ion keeps their name. The transition metals. So this is basically, the transition metals are everything past the alkali earth metals over to the staircase on the periodic table. Okay, so usually on the periodic table, there's kind of, you see a kind of this hard, bold staircase line that kind of divides the metals and nonmetals. So everything on the underside of the staircase is going to utilize this nomenclature. Okay, so the metal keeps its name, but we have to assign the oxidation state. Okay, so here's where the kind of the staircase thing usually is. It's kind of bolded right here, right? So it's kind of goes down around here. So everything on the lower part of the staircase is going to fall into this kind of nomenclature. All right, so that's where we left off from last night. Now we talk about covalent molecules. Okay, covalent compounds are nonmetals paired with nonmetals. All right, so again, the first element keeps its name. Okay, nitrogen doesn't change. The second element still has an IDE ending. Oxide, okay, chloride, fluoride, bromide. Okay, the second element has an IDE ending just like it did before. The only difference here is that we have prefixes that go with each element in the molecule. So the prefix tells us how many of them there are, how many of each element are there. So the covalent nomenclature is actually very easy because it literally tells you exactly what the formula is. Okay, one is mono, which we don't use often, okay? So it's not used, it's certainly not used for the first element, so we don't do mono for the first element. Okay, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Commonly, the mistakes are usually around the 6 and 7 range, okay? Because in other types of nomenclature, these are, you'll see a septa, right? So these are with an S instead. So in biology, sometimes you see like a septa, right? So instead of hepta, right? So commonly people mistake that and use the S versions, okay? So the first element keeps its name. We don't use mono if there's only one of them. The second element has an IDE ending, and we have a prefix that tells how many of them there are. So nitrogen, tri, 3, iodide. Now, it's okay for the double vowels here. Generally, we don't use, it's not wrong, okay? So if you did monooxide, it's not wrong, but generally by convention, we drop some of the double vowels just for how they sound. So it becomes monoxide, not monooxide, okay? So again, it's not wrong if you put the mono with the double vowels, it's fine. Usually for iodine, the triiodide, the double I's don't provide so much of a difficulty in pronunciation that one of them gets dropped. So we have one nitrogen and one oxygen. Nitrogen, monoxide, okay? So here, again, it wouldn't be wrong to put monooxide, just by convention, usually we drop one of the O's, okay? Here I have 2 nitrogens. So it's going to be dinitrogen. So 2 nitrogens, dinitrogen, tetraoxide or tetroxide. Okay, so again, the double vowels usually drop off with the O. It's not wrong to put tetra with the A. Call it tetraoxide. It's not wrong. Just by convention, usually we drop the double vowel. Arsenic or diarsenic, so the 2 diarsenic, pentaoxide or pentoxide. Carbon, tetrabromide. The tetra tells how many of the bromines there are. Tetrasulfur, tetranitride. Okay, so we're counting, we're telling exactly how many there are. Right? Now, there are a few of these where they don't fall into this standard nomenclature. Okay, there are a few that have common names. There are a few common name compounds, right, where their name is dominant over the IUPAC nomenclature. Okay, so NH3 is not nitrogen trihydro. Okay, its name is ammonia. Okay, it is not phosphorus trihydride, it is phosphine. It is not arsenic trihydride, it is arsine. Okay, can we think of another one? What's another one that you can think of that doesn't seem to fit within what we've been talking about as normal nomenclature for this? If you try Googling later, dihydrogen monoxide, right? Dihydrogen monoxide, right? Water, right? There's a bunch of spoof websites about dihydrogen monoxide. They're poisoning us with dihydrogen monoxide. They're putting it on our plants. Did you know they put dihydrogen monoxide in our drinking water? The government's out to get us. Look at all the horrible effects of dihydrogen monoxide. It dissolves all these molecules, right? So there's some funny websites that talk about the dangers of dihydrogen monoxide water, right? So H2O doesn't follow the IUPAC name. Okay. Another one that gets into more organic nomenclature is methane. So it is not carbon tetrahydride. CH4 is methane. Okay. All right, acids. This is our last section. So acids, there are 2. So before we can really get into the nomenclature for acids, we have to talk about what is an acid, because this is not usually something we don't get to acids until a later chapter. So this is naming things that we don't really know what they are yet. So acids, generally for our definitions, there are a couple different definitions for acids. In our case, an acid is a proton donor. A proton is simply a hydrogen. Okay, H plus is a proton. Hydrogen, as an element, has 1 proton and 1 electron. But if it loses its electron, it is just a proton. So it is called a proton donor. Okay, or it is called a proton when an atom donates it. All right. So H plus is considered a proton. So molecules that start with H, at least in general chemistry, molecules that start with H are probably a good giveaway that it is an acid. Okay, so there are 2 general kinds of acids that we're going to talk about. Binary acids, for example, HCl is a binary acid because there are 2 elements present. And oxyacids, where here we have an oxygen present. Okay, generally, in binary acids or in acids in general, they are generally aqueous. So you'll see this AQ listed after it. AQ just means dissolved in water, okay? So HCl, so it'll say HCl-AQ after. So it's HCl in water, dissolved in water, okay? Because you can have HCl gas, right? But the common way that you would look about that is like, you know, if you have HCl gas, then that means that there are only other HCl's around, okay? If you're trying to be a donor and there are only other molecules around that are also trying to be donors, who are you giving stuff away to? Okay. If I'm trying to give you money, okay, I can't say that I donate to some particular charity if I don't actually give any money away, right? I can't be an organ donor, really, unless I actually donate organs, right? Or a blood donor, unless I actually give blood, right? So HCl gas is a situation where there isn't anyone to give the hydrogen to, so HCl gas may not be considered an acid. It would be hydrogen chloride would be its name. But when we put it in water, there is now a water molecule present that the HCl donates its proton to. Okay, it actually gives the proton away to the water molecule. And so water accepts the proton. And so it becomes a donor molecule. Okay, so the naming convention for binary acids is hydro. Okay, the root part of the nonmetal with an IC ending and acid. Okay, so it's kind of a complicated thing, right? So look at HCl, okay? Hydrochloric acid. So it's not chloride here. So before all of our endings were IDE, so now it's an IC ending. So chloric indicates that it is an acid name. Okay, so it is not hydrogen chloride. Okay, hydrogen chloride would indicate that it is the salt hydrogen chloride or the gas hydrogen chloride. But hydrochloric, the IC is telling us that it is an acid name. Okay, plus you put the acid in there as far as the name, so it's hydrochloric acid. So generally we include acid in there, but people get lazy and leave the acid part off. But the IC is enough to tell us that it is an acid. So hydrochloric is enough to tell us that it is an acid because of the IC. Okay, so these are also binary acids. Again, by binary, that means there are two elements, not that there are only specifically two of them. Okay, so HF would be hydrofluoric. Okay, fluorine has the root fluoric acid. Hydrofluoric acid. H2S, so it is still a binary acid because there are two elements. It just happens that there's extra hydrogen there that balances out the sulfur, but it is still a binary acid. So it is hydrosulfuric acid. HI would be hydroiodic acid, the IC. So hydro, the root part of the name, and an IC ending. Okay. Our oxyacids, so this is another one of these places where knowing your polyatomic ions is going to be helpful because the polyatomic ion name gets modified to make the acid name. Okay. NO3 is the polyatomic ion nitrate. So when you pair that with hydrogen, the ATE gets replaced with an IC, and so it becomes nitric acid. Okay. So if you don't know the polyatomic ion, then it is hard to, if you don't know the polyatomic ion's name, then you won't know what to change it to as an acid. Okay. NO2 is nitrite. So any polyatomic ion with an ITE ending, starting with H as an acid, ITE becomes OUS. So it becomes nitrous acid. Right? We'll come back to this chart later. So this is really just looking at other polyatomic ions in the same family. Okay, so you would have memorized these, right? So these ones, so these are the ones that I gave you to memorize, the chlorine ones. So perchlorate, chlorate, chlorite, and hypochlorite were polyatomic ions that you should know. But if I swap out the chlorine with a bromine, it has the same name. It is hypobromite. It is perbromate. The number of oxygens here, okay, their charge is going to be the same. So the oxidation state for the nonmetals are the same as long as they have the same number of oxygens. So that if they have the same number of oxygens, they have the same oxidation state, then they have the same name that goes with them. So this means that if you know one set, then you can derive other sets in the same family. Okay, so these would be polyatomic ions that you wouldn't memorize, okay, that you would have the first set memorized, and we can just alter them to make the others. Okay, we'll talk about how we get the name here shortly. All right, we'll do that at the end. All right, so naming these acids. PO3 was not one of our polyatomic ions. So PO4 was phosphate. So PO3 is phosphite. And so the ITE becomes OUS. And so this is phosphorus acid. So this would be, it'd be the phosphite.
So you would just ignore the hydrogen part of the name?
Right. For the oxyacids, we ignore the hydrogen part of the name. Yes. So it is more important about the polyatomic ion. Okay. So the sulfur here, or the sulfite, becomes sulfurous acid. So you can see right here, it's not quite an exact exchange of ITE to OUS, right? Because this would be sulfite. Then so the sulfite doesn't become sulfus, right? So it has a slight tweak. I think it's more for pronunciation than anything else. So this is where just seeing practice problems, seeing where there's kind of some weird change and the name is not exactly one-to-one. So I mean, nitrate becomes nitric, nitrous, or nitrite becomes nitrous. But for sulfur, it's not, the sulfite doesn't become sulfus, right? So it becomes sulfurous. Okay. IO3 would be iodate, so it becomes iodic acid. ATE becomes IC. And this is a binary acid, so it is hydrobromic acid. Right. So this is kind of a summary chart. I don't know how beneficial this slide is, but it is here. Okay. So let me do one thing real quick here. So